So in this video we're going to continue our discussion with complex numbers, and we'll start with de Moivre's theorem. But before we get to the theorem, let's recall from the other day that when we multiply two complex numbers, z1, z2, that we come up with the r1, r2 cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. We proved that the other day. Now let's go ahead and let z in general be r cosine theta plus I sine theta. Just a general understanding that that's our trigonometric form of a complex number. And so if we take z squared, that's really just going to be this thing here multiplied by itself. And we know that when we multiply two complex numbers, we end up with this formula right here. So now, if we do this, we get r times r, we get cosine theta plus I sine theta plus theta. And we can simplify this down a bit to r squared cosine 2 theta plus I sine 2 theta. So only having one r, only having one theta, we can combine it into this. If we went to z cubed, as you can probably imagine, you would end up with r times itself 3 times, so r cubed, and then cosine and theta plus theta would give us 3 theta plus I sine 3 theta. So we can continue this as far as we would need to, but de Moivre's theorem is a generalization of this. If we have z to the nth power, that's going to be r to the n times cosine n theta plus I sine n theta. So we're now allowed to generalize complex numbers to a higher power as this formula right here. Okay, so in the first example here we look at, we've got, looks like z to the 7th. So z to the 7th would give us r to the 7th times cosine of 7 theta plus I sine of 7 theta. So it's up to us now to find r and to find theta. And so if our z is equal to negative root 3 plus I, then the r can be found the same way it has always been found, when we take the a squared plus a b squared, all square rooted, and the r value here comes up to be a 2. And for theta, we'll take tangent of theta, which equals the y, or the b in this case for a complex number, I'll say that, 1 over negative square root of 3. Now here's where we'd want to be a little bit careful. Notice that our point in the complex plane would be negative root 3, positive 1, so that actually puts us in the second quadrant. So if I go ahead and I draw this as the real axis and this is the imaginary axis, then our point is going to be up here, allowing us to draw the triangle with a 1 and a negative root 3 respectively. So that would give us a 2. That would also give us a reference angle of pi over 6. So then theta looks like would be pi minus pi over 6. In other words, theta equals 5 pi over 6. So I'll go ahead and I'll take my r value, I'll take my theta value, and I'm coming right back into this right here. So let's see, we've got our r value 2 to the 7th times cosine, and when I multiply the theta by 7, I get a 35 pi over 6 plus I sine 35 pi over 6. And the 35 pi over 6, notice how that's unnecessarily large. So what we would try to do is find the least positive coterminal angle for the 35 pi over 6. So if you go ahead and you subtract out multiples of 2 pi, you'll end up with the 128 cosine of 11 pi over 6 plus I sine of 11 pi over 6, which we then could simplify down. So over here to the side, we'll have our 128, and then cosine of 11 pi over 6 would be a root 3 over 2. And then we have our plus I sine of 11 pi over 6, which would be a negative 1/2 I. And then finally, when we distribute the 128, we'll get 64 root 3 minus 64I for our final answer. All right, so now we're ready to talk about the nth roots of a complex number, which initially seems a little bit messy, but once we take a look at the first example, it's actually a pretty useful and interesting tool. So the formula for the nth roots of a complex number would be r to the 1 over n times cosine of theta plus 2k pi over n plus I sine of the same theta plus 2k pi over n. Now, the k's would equal 0, 1, 2, all the way up to n minus 1 of them. And again, it looks a little messy, but let's take a look at the first example and I'll show you how it works. So the first example we'll look at, they're telling us to find the fourth roots of 1. Now, anytime you see the phrasing roots of 1, this is also something called roots of unity. So roots of 1 and roots of unity are the same thing. Now, to get things started, let's identify what it is we know. Well, the fourth roots of 1 means 1 is our complex number. So our z would actually equal 1 plus 0i. It also means that we're going to need r and we're going to need theta. Well, from this complex number, we could see that r is simply going to be 1, and our theta is going to end up equaling 0. If you picture this on the unit circle, however you need to see it, even in the complex plane for that matter, you can see your theta would equal 0. Now, it's fourth roots of 1, which means n is equal to 4, and we would want k values of 0, 1, 2, and 3. So now, once we identify all of this, it's just a matter of plugging it back into the formula. So for k equals 0, we have 1 to the 1/4 cosine 0 plus 2 times 0 times pi over the n value of 4. So I'll write the same thing down for the sine. And you can see, I'll point it out to you again. So we have our r value raised to the 1 over n cosine theta plus 2k, in this case k is 0, pi, all over the n value of 4. And this guy and this guy are the same. Now I'll keep going with k equals 1. So we'll pretty much have a lot of the same stuff. The theta value is still 0, but now the k being 1 changes it slightly. So I'll go ahead and write this one down as well. And I'll do the same thing now for k equals 2 and for k equals 3. So we'll have a 1 to the 1/4 times cosine 0 plus 2 times 2 pi over 4 plus I sine of the same thing. And then k equals 3 would be our last one that we needed to do. 0 plus 2 times 3 times pi over 4 plus I sine of 0 plus 2 times 3 times pi over 4. So that's actually the hard part, is to getting it set up. So now we're ready to evaluate, and feel free to take a little bit of time and slow down if you need to here. But when we evaluate this, you would find out that this first one gives us a 1. The second one gives us an I. The third one gives us a negative 1. And the fourth one gives us a negative I. Now, I'm going to go ahead and clear the screen, but remember these answers right here. These are the answers that we came up with for the fourth roots of 1, and I'm going to show you now a little bit of a different spin on it, how it's all related. Okay, so to show you exactly what it is you found and to understand a little bit of how this all connects, I went ahead and I've said that x now, in a more algebraic sense, equals 1 to the 1/4, so the fourth root of 1. Now, if I go ahead and algebraically manipulate this by raising both sides to the fourth power, that's going to give me an x to the fourth equals 1. I also then can move the 1 to the other side. And then in solving this algebraically, this factors into x squared minus 1 and x squared plus 1, which the difference of squares can be factored again into x plus 1, x minus 1. The sum of squares stays alone. And then if I take each one of these factors and set it equal to 0, you can see x would equal negative 1, x would equal 1, and then when I move the 1 to the other side and I square root the negative 1, I get x equals plus or minus I. And those are the same four answers that we came up with the trigonometric way. For us, it's a great way to relate some things we've done in the past, what we're doing now, but it's also helpful to have these tools for some things where algebraically speaking, we wouldn't be able to do what we just did. All right, so taking a look at this example, we'll go ahead and we'll have to first manipulate this thing to understand better what it is we're looking to find. So the first thing I'm going to do is get the x cubed all by itself. So to do this, I'll I'll add I to both sides. I'll subtract 2, and then I'll divide by I. Now, I do want to go ahead and rationalize this, so I'll do an I over I. And distribute that through. So we find x cubed equals I squared minus 2I over I squared. We know that I squared equals negative 1, so this would be a negative 1 minus 2I over negative 1. And finally, x cubed would equal 1 plus 2I. So from this step right here, you can see that we're going to look for the 3 roots of 1 plus 2I. So that's really the question there that we're trying to solve. So let me go ahead and erase some of this and clear the screen so I can have some room to work here. So we're going to go ahead and working with this complex number, we're going to need to find r. We know that r is going to be the square root of 1 squared plus 2 squared. So r equals the square root of 5. We're going to need theta. Tangent of theta in this case would just be a 2 over 1. Now, that's not one that we know, and so I'm just going to say that theta equals the inverse tan of 2. And if you'll notice in the instructions it says solve but do not simplify. I'll show you what we mean by that as well. It looks like the n value would be 3, and the k value then would have to be 0, 1, and 2. So to get started here, for k equals 0, we would have our r value raised to the 1 over n. Then we'd have cosine. Our theta now, remember that's going to be our inverse tan of 2 plus 2 times 0 times pi all over the n value of 3. And then the same thing for sine. Our theta is going to be exactly the inverse tan of 2 plus 2k pi all over the n value of 3. So there's k equals 0. For k equals 1, we're going to have the square root of 5 to the 1/3 again. Cosine inverse tan of 2 plus 2 times 1 times pi over 3 plus I sine of inverse tan of 2 plus 2 times 0 times, 2 times 1 times pi all over 3. And finally, we'll have k equals 2. So the square root of 5 to the 1/3 cosine inverse tan of 2 plus 2 times 2 pi all over 3 plus I sine inverse tan of 2 plus 2 times 2 pi all over 3. So I would consider this far enough to at least to go in the video. You'll get some practice at home with your calculators and punching this stuff in, but for the sake of our discussion, the setup is there. We've got all the parts labeled correctly. At this point now, it's just a calculator problem.